in Unit 2, we introduced this method for handling quantum transport, this general method. And what we're doing in this unit is looking at different examples to get a better feeling for how to apply the method. And the first example we'll look at is this very important example about quantum point contacts. Now, what's a quantum point contact? Well, a point contact means, like what I've shown here schematically, that current flows from left to right. You have this applied voltage, but they have to squeeze through this narrow region, because these black regions, what you have done is by putting a potential on these gates, you have depleted the conductor underneath it. And so all electrons have to squeeze through this region, and so the conductance is largely determined by this narrow region. And since this narrow region is fairly short, what you measure is the ballistic conductance of a region whose width is this W, which is this little white region through which the electrons have to squeeze through. Now, as we discussed in part A, what you'd have expected is that this conductance, this ballistic conductance, would vary linearly with the width. Because ballistic conductance doesn't depend on the length of a conductor, but it sure depends on the cross section. So this is what you'd have expected, and there were many experiments in the 1970s, where people had seen this, and this is generally what's referred to as the Chardin resistance. But what had a major effect on this field was a series of experiments starting from 1988, which showed that in small conductors, what you see is a conductance that doesn't change linearly like this, but rather it goes in steps. So this is one of the experiments from one of the groups which appeared in Physical Review letters. And around the same time, similar results also appeared from a different group in a different journal. And I've just shown this one. What it shows is the resistance versus the gate voltage. So what the gate voltage does is changes the width of this narrow region. So this axis you could view as W. It's the width of your ballistic conductor. And you can see this resistance shows these steps. And when you subtract out the series resistance of the surroundings and invert it, you get the conductance. And what you see is this conductance goes in steps. And it can be expressed as this quantum of conductance Q squared over H times 2 for spin, because usually these modes or channels, they always come in pairs. Anytime there's an upspin, there's a downspin that goes with it. That's the 2. And then M is the number of channels. So this was a seminal experiment, because this quantum of conductance, I guess since then, has become is an integral part of our general discussion of nanoelectronics and mesoscopic physics. Because this idea that conductance is this quantum of conductance times the number of channels. And experimentally what you're seeing in this ballistic case is these steps. So this is a very important experiment, a very important physical phenomenon. Of course, in this context, I'm just using it as an example where you can try out the method for quantum transport that we have discussed. Because whenever you have a new method, in general, the principle is apply it to a problem where the results are well known and make sure you get the correct results. Before you go off and do problems where you don't know the answers. And so I always suggest this as a very good example to start from, because if your method works and you have set it up right, then you should be able to get this quantized conductance. So how would you do this? Well, if this was a one-dimensional problem, then you could do what we discussed in the last unit. That is, set up this one-dimensional tight-binding model with the diagonal element epsilon and the nearest neighbor coupling is T. And so the H, the Hamiltonian, would look like epsilons on the diagonal and T's on the lower and upper diagonals. And if you want the Sigmas, well, for the one-dimensional problem, we had discussed in Unit 2 that the sigma looks like e to the power ika. It is non-zero only for the boundary points. So at this point it's non-zero, so it's t to the power ika, the rest of it is all zero. Here also it's t to the power ika for the first point, rest of it is all zeros. And what's k? Well, that's related to the energy, and you get it from this dispersion relation for the leads. E is epsilon plus 2p cosine ka, and you can invert it to get an expression for k. So this is how you could write down the h's and the sigmas. And of course, once you have them, you can use the general equations that we talked about. This is coherent transport, so you could just calculate the transmission. Now, if inside you happen to have a barrier, let's say it's not a uniform conductor, but there's a barrier there, well, you could include that as well, because what it means is that the diagonal element for that point would have an additional u, that's the barrier. So what that means is, to the h, you'd add another matrix like this, which has a u at the second point, for example. Because here I'm kind of showing it as if the device has 3 points, so the u is in the middle. So the point is that numerically, the process is quite straightforward. You could have any potential inside, you can easily include that in the h, and you can write down the 2 sigmas, and then you can calculate anything you want. But the thing is, this is a 1D example. What we need to do is the 2D version of it, because 1D will not capture the physics of this. Now, for 2D, you need to start from a 2-dimensional lattice. Again, the diagonal elements are epsilon, the nearest neighbor coupling is t. Now, if you want to include this point contact, what you could do is put in something like this, where on these sides, you could add a u. The same way we added a u in the 1D example. So that way, you can put a very big barriers here, so that electrons can't even get near it. And that thereby the electrons would have to squeeze through this point contact. So numerically, that's how you could include, or you could make this structure look like the physical structure that you are trying to simulate. So that would be part of the H. Now, you then need the contacts, and you have to be able to write down the sigmas. And that's what I'd like to explain next, is how you write down the sigmas. Because what we discussed in Unit 2 was how to write down the sigmas for a 1D problem. Now we have a 2D problem. How do I write down the sigmas? And what you'll see is that in this case, by using a clever trick, you can extend our results from 1D to write down the results for 2D. So let me explain how you do that. So the way it would work is, let's say, just to be clear, we take 3 points along the way, and you want to find out this sigma. So this is the actual device side, and it's connected to this side, and you want to write down this. Now, what you could do is, when you're trying to visualize this H matrix, it is convenient to think of this column as one unit. You see, this is a 2D problem, and a very good way to do the bookkeeping of how when you're setting up this H. Because in 1D, it's relatively easy to set up the H. In 2D, the bookkeeping isn't completely obvious. But in other words, it's not even unique. There are many different ways of doing it. But the one I found most convenient is to think of this column. I've shown here 3 things. There could have been 10 things there. But that column is one unit, which I call alpha. And the coupling of this unit to the next, that's what I call beta. So this alpha itself is a 3x3 matrix. You see, usually in 1D, epsilon is a number, t is a number. But now, this kind of looks 1D, but the point is, instead of epsilon, I actually have a 3x3 matrix there. And the beta is a 3x3 matrix. Okay? And this is a very good way to visualize what's happening here. Now, how would you write alpha? Well, alpha is basically this 1D chain. So alpha would look something like this. Epsilon's on the diagonal, and t's connecting it to the nearest neighbor. So t's So that's it. So this is alpha. How would you write the beta? Well, beta is the connection from one column to another. And there you notice the connection is from point 1 to point 1, point 2 to point 2, point 3 to point 3. And so beta looks diagonal. It's just T's along the diagonal. It connects 1 to 1, 2 to 2, and 3 to 3. Now comes the important point, and that is that what you can do is do a basis transformation so that in the new basis, alpha becomes diagonal. Because this is not a diagonal matrix, you've got off-diagonal terms. But you can always diagonalize the matrix by using the eigenvectors of alpha as your basis. So the general procedure is that if given an alpha, you can find the new alpha, which I've indicated with a tilde, by finding an appropriate transformation matrix V. So if you're doing it numerically, there's a command in MATLAB or in any other software that you're using, which will allow you to do that, which allows you to diagonalize this matrix. It will tell you what this transformation matrix should be. Of course, by hand, analytically, if you want to find it, that's also straightforward. It's something you can look up a linear algebra book if you want to see how to find the V's. But once you have that, then, see, you could transform this alpha from this off-diagonal and get rid of these off-diagonal terms so that it looks diagonal. Now, one point though is that you see in our model we got two matrices, alphas and betas. And usually often what happens is if you diagonalize one of them, the other one may not remain diagonal. And so it doesn't help because, of course, whenever you're solving a problem, all matrices need to be in the same basis. But here the advantage is because this beta is like an identity matrix, it's the same T everywhere. So what that means is when I change basis, the identity matrix always stays identity. And so in the new basis, we still have exactly the same beta. And so in the new basis, alpha is diagonal and so is beta. And what that means is that you can visualize in this new basis, which are called the eigenmode basis, you can visualize the problem in terms of these new alpha, the alpha tilde, the beta, and they're all diagonal. And what that means is it's like separate 1D wires. So this wire has a diagonal element of epsilon 1 and the connection is T. The next wire has a diagonal element epsilon 2, the connection is T. Epsilon 3, connection is T. But the point is there is no connection in this direction, unlike the original problem. The original problem had connections going this way. Now there's no connection in this direction at all. And so the original 2D problem has now decoupled into a set of parallel 1D problems. And what that means is, of course, that since there are parallel 1D problems, I can do them one at a time. So what I can do next is, I can write down the sigma for these 1D problems using what we had learned in Unit 2. Remember, what we learned in Unit 2 is that sigma is given by T e to the power I k a for the boundary elements, and it's 0 for the rest. So we just focus on the boundary elements. So for 1D, you would have got a T e to the power I k a. Now what happens is you've got a whole bunch of things in parallel. So you get T e to the power I k1a for wire 1, T e to the power I k2a for wire 2, T e to the power I k3a for wire 3, and so on. And how do you find these k's? Well, they're related by this dispersion relation, when E is epsilon 1 plus 2t cosine k1a, or epsilon 2 plus 2t cosine k2a, etc. So you can determine k1a or k2a from the old formula, except that each wire gives you a different k. They all have the same energy, E, but the k's are different because the epsilons are different. So the point is, in this basis, you have managed to write down the sigma. So does that mean we need to solve the problem in this new basis? Well, not quite. Once we have this, you could always transform it back. Because just as you can go from the original lattice to the eigenmode, you can always go backwards. Take the eigenmode representation and transform back to the lattice representation. And the method is, here if you had a V dagger and a V, here you go V and V dagger. Right? This is the standard principles of basis transformation in linear algebra. So here we have the sigma in the new basis, in the eigenmode basis, so you could just transform it back. And you'd have the sigma in the lattice basis where we want to work. So what we have done is, by using this very clever method of basis transformations, we have managed to use the 1D results that we learned in Unit 2 to do a 2D problem. Because we took the 2D problem and, doing a basis transformation, decoupled it into a bunch of 1D problems. And this is conceptually a very important thing, because that's essentially what you mean by modes. That when you have a conductor with a cross section, which is not a 1D conductor, like a 2D conductor or a 3D conductor, you can think of it as lots of modes in parallel which are all decoupled. So the mathematical basis for that is this diagonalization of these alphas. Now, you could use this method now to numerically simulate a structure like this. And if you're doing it on a computer, that's all there is to it. So you set up the H, you write the sigmas, and then you use the formulas we have discussed earlier. Now, if you want to understand it, then this one is not so straightforward. What you can do is think of a couple of related problems where you can see the answers in a relatively straightforward way. You can kind of see why you'd get this quantized conductance. The point I'm making is, if you just set this up on a computer and you have done it right, you should get this quantized conductance straight out of the simulation. And that's a very good way to check your simulation, because, as I said, you don't get steps by accident. It means you have done it right. On the other hand, if you want to understand why it looks like steps, then it's easier to think of related problems like this. That is, supposing instead of this gradual constriction, we think of something like this, where it's uniform width everywhere and equal to the narrowest region. Now, you might say, well, that's not the real structure. Real structure has to widen so that in these regions, they are very highly conducting. And you can actually assume that the chemical potentials are constant. Right? So you actually need these wide regions in general. But for doing this problem, you could assume that you have this narrow region connected to regions which are not widened, but is exactly the same. And the reason this works, or gives the results, the same results as you get from the wide case, is that both have this important property, that when an electron comes from here, in this uniform structure, there is no reflection, because it's a uniform structure. The electron just goes straight out. And the real structure, where it broadens, there also there is not much reflection, unless the energy happens to have certain specific values. So in general, electrons, when they try to come out in the original structure, they don't have much reflection either. So it's that reflectionless context that's important in order to get nice clean steps. And so, if you assume a structure where there's no reflection because it's uniform, you get the right results. And often that's a much easier problem to simulate than the real one. Of course, as I say, if you just went ahead and simulated the real one, you would get the steps. Now, how do you understand this uniform structure? Well, in this case, the way you can think is, I got multiple wires, multiple 1D wires. So what is the transmission of one of these wires? Well, the idea is, if you looked at the first wire, you would get a transmission which would be 1 over a range of energies of 4T, and where the center of it is epsilon 1. Similarly, the next one would be the center around epsilon 2, and the width would be 4t again. Epsilon 3 and the width would be 4t again. And where does the 4t come from? Well, that's the width of the dispersion relation. E equals epsilon plus 2t cosine k. So each one of these then has a band where the transmission is 1 because it's a ballistic conductor. This band is again 1, that band is 1, but the bands are offset. And so when you add these up, because all of these are in parallel, so when you add them up, you get these steps, like so. Incidentally, I wrote here T, whereas here I've written T0. It's really meant to be the same thing. Now, what is the actual transmission that determines the measured conductance? Well, at low temperatures, it is determined by the transmission around the Fermi energy or this chemical potential. So if your mu happens to be here, you have that value. And as you change the width of your conductor, what would happen is these epsilon 1, epsilon 2 would move around. And so you may be here at some width, and then if you make it a little narrower, this edge might move up so that effectively you could be at this value. So as these edges move, you would be going from one integer value to the next. So you could actually set up your computer to calculate this transmission at a given energy as you change the width of your conductor. Because as you change the width of your conductor, the epsilons change. And as the epsilons change, the transmission at a given energy changes. And that is kind of what you actually measure experimentally. So this would be how you could try to understand what you should be getting out of the computer once you set this up numerically. Well, that kind of brings us to the end of this example, this quantum point contact. And as I mentioned, what allowed us to do this was this clever idea of basis transformations, which worked only because when we diagonalized alpha, beta remained diagonal. And the reason was beta had this very special form. So when you transform basis, it doesn't change. But this property is not true in general. So in general, if you try to diagonalize alpha, beta won't stay diagonal. And so we need a more general method that we can use in any problem. And that's what we'll be doing in the next 2 lectures. So we'll be setting up the general method for finding the self-energy sigma. Thank you. So, I wanted to stop it at a point where you could see this thing. So, I guess what we went through was this example where you could diagonalize this, and because the beta was an identity matrix, it stayed diagonal. Now, and a very good example to go through is this quantum point contact, because whenever I'm trying to set up this NEGF for a new material, I'll always try to do this ballistic example and see if I get steps. Because usually there will be some small mistakes, and the steps are something you have to do everything right to get it. Otherwise, it never works. But there's always a very good example to start from, just the ballistic case. Do you get it? And then after you have the ballistic case, then you can put in scatterers, etc. Now, this method doesn't work in general. And 2 good examples that show the more general method are like calculating the ballistic conductance in graphene, and also calculating the ballistic conductance in a magnetic field. Those both are cases where alphas and betas are such that you cannot really diagonalize them at the same time. So this idea of the basis transformation doesn't quite work. And there's a more general way of doing this, which is this idea that sigma is equal to, so let's say this is the device and you are cutting it off here. So this is H, and this is, you want to write down the sigma that goes with this. that sigma is beta G beta dash. So beta is this coupling going this way, and this G is what's called the surface Green's function. And what's the surface Green's function? Well, what it is that here, of course, this is an infinite wire. So let's assume you cut it off here. So it's an infinite wire and this is the surface. Now, this infinite wire, of course, if you just looked at the Green's function of this infinite wire, which is E minus H plus I eta inverse. If you looked at that, it would go on forever. This would be infinitely long. But what we want here is just the first element, the one that corresponds to this surface point. Now, which of course could be just a number, or it could be, so you could have, say, 10 basis functions per unit cell, in which case this itself would be a 10 by 10 matrix. The point is, it's just the surface thing. That's what should go in. So this is the more general expression. And for those of you who have had some quantum mechanics, you have probably seen something called Fermi's golden rule. So, and it's a little bit like that, in the sense that Fermi's golden rule, you write rate of scattering as density of states times matrix element squared. But point is, this is exact. These are like the matrix elements, beta, beta dagger. And this is like the density of states. The Green's function is like the density of states. So it's a little bit like that. But anyway, so this is, though, there's no approximations here. Not like Fermi's golden rule. It's not like this is the first order theory or anything. It gets you exactly the right answers. So maybe we could go through a little bit of that lecture, because that lecture explains where this relation comes from. This sigma equals beta G beta dagger, because that, I think, is a much more general thing that you could use. In general, whenever you are even, say, trying to find the self-energy due to electron-phonon interaction, it is this one that you would use. This is the one that would more readily use. So let me just play that a little bit. But before we go on, maybe if you have questions on this, please go ahead. Okay. Yes, please.
So when we kind of separated all the 2D number of atoms of diagram, the sigma matrix that was an identity matrix with e to the power ik on the diagrams.
Not identity matrix.
Yeah, K1, K2, K3.
Right. Identity would imply that all are equal.
Yeah.
Here it wasn't equal.
Yeah, so when we were writing this matrix for a 1D case, we were keeping either the first or the last element to be to the power ik8. That conveys that the first and the last atom or whatever is connected to the previous and the latter one. But in this case, it doesn't convey the same thing.
Very good point. So here we are doing this wire. Okay. So let's say you had a wire with the 3 of these, K1, K2, K3. And let's say along the length you got 3 points. So generally I should have written a 9 by 9 matrix. But what I wrote here is kind of just this part. If you wanted the full 9 by 9, you should fill it up with 6 by 6 zeros up here. Because this is just this end of it. Or another way of thinking, so just depends on how you are doing your bookkeeping. So if these 3 are kind of in this corner and then the next 3 and then the next 3, then it would look like this. Or you could do it this way, in which case it will be 0, 0, t to the power ik1, k, then 0, 0, t to the power ik2, etc. Yeah, very good point. Glossing that over.
So after doing this, we are converting it back to the lattice spaces. But why can't we just solve in the eigenvalue?
You could do that. And then your H matrix should also be in the eigenbasis.
So will not that be much easier than this to solve numerically?
Right. So it is just that when you are setting up the problem, the H is already in the lattice basis, and then you write your sigma as t to the power ik1, ik2, ik3, transform, and then you have it in the lattice basis and go on. But you could just as well take the H and try to go the other way. Yeah, either way, I don't think makes much difference in terms of computational time or anything. So a lot of these things, as far as the computer is concerned, are all the same. As far as understanding is concerned, one of them is much easier than the other, because anything in which matrices are diagonal, we can understand easily. Anything when it's not diagonal, not very easy to understand.
Sir, we are writing sigma for one point of line, right? So when we are solving the actual device, we would have to construct the potential profile before applying it here. So we have to construct the potential profile before applying it to NGF, right? So kind of a steady state profile, and then we compute the current.
The profile meaning the
With
potential.
Poisson and self-consistent.
Right. So one thing in general I have not been stressing is if you are doing device simulations, then you have to set it up self-consistently with Poisson equation. Right? But for linear response calculations, which is like low voltage, you do not need that, which is kind of what you are doing here.
So if we set up only 1 point for sigma, then convergence in Poisson will be very difficult because
1 point for sigma?
we are considering contact for 1 point, right? Here.
No, meaning the device. Rather, I'm not getting what you mean.
If you have simple source, drain and channel device, so
So it's, I guess what I've drawn up there, let's think of this one. Yeah. So generally your device would look something like this. And then your sigmas would go here, sigmas would go there, right? And this would be the device.
so if you have a large device, right, like 100 points in the channel, then ideally what should the contacts be like?
Yes, but the sigmas will be non-zero only for the last point. Sigmas will be non-zero only for the last point. And then you will have as many points as you want here. In between. That will be the real device. And the potential would have some profile inside. That will be the full device. But in general, yes, there's this Poisson equation that has to be done self-consistently. And that part, because it is self-consistently, there's convergence issues, and there are again good methods. People use this Newton-Raphson method for doing the Poisson part of it. Right? Whereas here the examples I'm showing you are all just low bias, so you're not worrying about Poisson. Here. But I think again I have a few MATLAB codes in there which do the Poisson also, if you want to.
First is slightly long device. Can it 2 points instead of 1 point in the contact? Is there any computational problem?
2 points meaning?
Inside the sample, so you are taking only sigma non-zero for the last point.
Oh, sigma should be non-zero only for the last point, as long as it is the nearest neighbor tight binding model.
So if I go beyond the nearest neighbor tight binding, then I can take 2 points.
Then it's 2 points. Then actually conceptually, you are better off probably taking 2 of them and viewing it as 1 unit, so that the connections are still nearest neighbor, unit to unit, I think. So, because a lot of the models I'm familiar with are usually nearest neighbor models. And if it is nearest neighbor, then the only non-zero sigma would be for this one, because that's the only one that has a direct connection to the outside. But if it is next nearest neighbor, then this has a connection and this also has a connection. And there, I think people who do it, they would usually probably take that as one unit. Because conceptually, as I mentioned, when I draw one point here, that doesn't necessarily represent just one point. It could represent s orbital, p orbital, etc. So it itself could be a matrix. Could have 10 components to it. So conceptually, you can kind of take this whole thing and call it one unit. So finally, you sort of want a picture in your mind that looks like this. The units are alpha and they are connected by betas.
So that should be another sigma 0, right? Two units that
Which one?
that unit, what you are taking, which will include the nearest neighbor plus next nearest neighbor, that's another sigma 0. Will it be sigma 0 or is it the part of the contact? And you
So
take
I
this
will-
thing-
So in this context, it would be, let's say you have 2 points only in your device. So then this whole thing becomes the device, that's one unit alpha. And then there's the beta that connects it to the contact. And that beta does not extend beyond 1, doesn't go to the next one at all. Because you see, if this was your alpha, then there would be these connections. But since I made the unit bigger, the connections are now only nearest neighbor. So finally, I think for visualization, it's easier if it is nearest neighbor always.
The other-
So take a bigger unit cell if needed.
Self-energy, you said you can deal with electron phonon, right? But I guess it should be okay with electron also, right?
It's just that the electron, here, it should be.
The small device, the electron more important than the electron phonon, right?
Sort of, right. It is just that when you do a low energy, if you're just doing current flow, electron-electron interaction usually doesn't affect the current very much. And the reason is, whatever momentum one loses, the other one gains. So as an ensemble, the momentum doesn't change. That is why zero order, when we say mobility or conductivity, you'll notice that the electron-electron interaction doesn't enter that at all. It's a momentum relaxation thing. On the other hand, it does affect the phase relaxation enormously. And that is why things like Aharonov-Bohm effect, weak localization, all those are very much affected by phase relaxation time, and phase relaxation comes a lot from electron-electron interactions. And so, to include that in the model, one should have electron-electron interaction. But there again, I think it is simpler to put it in phenomenologically. That is, rather than the actual microscopically what the sigma should look like. That is much harder because it involves product terms and all
So
that.
that means you add a U to your epsilon again for electron interaction.
Right, but if you just add U in the Hamiltonian, then it won't be relaxation, it would be more like a coherent thing. What you want to do is put it in a sigma 0.
Now, what is in my mind, suppose in the small device, your transmission, in case of scatter, your transmission power will be hugely affected by the large electron-electron interaction, right? In a very small device, if there is a scatter, because potential profile will be completely changed and you have to do it self-consistently. How?
The electron-electron interaction is what you are generally including through this Poisson equation, and Poisson is like Hartree approximation, but you may need exchange correlation corrections. So that's what people do here. Now, if you had really strong interactions, then you could get into Coulomb blockade regime and all that. And in that case, it wouldn't come out so naturally from MEGF. There would be tricks needed to actually get the sigmas, separate issues altogether. But as long as but that is important in Coulomb blockade where electrons don't flow freely through the structure, so they end up spending a lot of time right there. But usual devices when electrons flow freely, then Poisson equation seems fine.
So it will be like a smoothing effect only, just not like a new effect kind Coulomb blockade.
And doesn't seem to affect the low bias conductance, linear response part. But in the Coulomb blockade regime, that's different. Okay, so I think in these lectures, there's probably one lecture which is called Does NEGF Include Everything? And in that one, I think I talk about this Coulomb blockade part, what is involved. Yeah. Any other questions? Please go ahead.
Sir,
Yes.
in device simulations, people often take the wave function penetration into the outside. So there will be points in the outside which will be part of my NEGF domain. So while calculating the self energy or sigma, do we have to take points in the outside as well for determining the self energy?
So ordinarily the self energy, we'll be setting up the, so what I had here, for example, these regions where you're putting a big U, those are kind of like your outside. So as far as the device is concerned, just put a big U there. That would more or less take care of it. The self energy comes in wherever electrons are actually going in and out of the system. So as long as, now of course these days with many small devices, one of the problems is that the insulator is leaky. So you actually get gate currents. Then there would be effectively a sigma that you need to describe that part of it, where you're losing electrons. But otherwise, usually the gate part of it is something like this. You just put a big potential there so electrons don't go there. That would be part of the range.
Excuse me, sir.
Mm-hmm.
Sir, instead, like this is a regular square lattice thing. So if I were to assume I have a structure in which the second layer is shifted by half the bond length, so then how are you gonna use this method? Because then there will be like two different interactions.
So actually graphene is a good example of that. So let me just play a little bit of the next lecture which talks about this method, because this is the method that's more generally applicable. Okay? And it kind of gives you a little better feeling for this sigma also. So let's look at that a little bit, and then maybe we'll look at a graphene example. Okay? A very important piece is to write down the self energy for the contacts. And in unit 2, we saw how you could do that straightforwardly in 1D problems. Now, in the last lecture, we discussed a 2D problem whereby using the method of basis transformations, you could apply this 1D technique to this 2D problem. But this approach doesn't always work. And so what we need is a more general method. And so what we'll be doing in this lecture is to develop this general expression for the self-energy that you can always use. Now, before we get into the general method, let me just quickly recap what we had done in unit 2 for the 1D problem. See, what we did was we said, let's say we have a 1D wire described by the Schrodinger equation E psi equals H psi. And then you impose these boundary conditions. That is, you assume there's a wave incident from the left contact, and there's a reflected wave and transmitted wave. And by applying those boundary conditions and eliminating the points outside the boundaries, you can get these additional terms. This one that represents outflow and the one that represents inflow. And what we showed is that the expression for sigma has this form where it is 0 for all points except the boundary, and at the boundary it's t to the power I k a. And the source term gain is 0 for all points except the first point where the wave is incident. And this B is the amplitude of this incident wave, which is related to the Fermi function. So using these results, we obtain these expressions for sigma and sigma in. That is how to write down these self-energies for the contacts. Now what we want to do is a more general 2D version of this. And the way we'll do this is, think of it like we have a device and it's connected to two contacts. And for starters, let's assume the device is not even connected to the contacts. So device is just by itself and is described by a Hamiltonian H. So that's this middle point, E minus H, times, if there was a wave function psi, it will be E minus H times psi equals 0. What we are assuming is that to start with, the device is empty. And then we have the two contacts, H2 described by H1 and H2. And we are assuming that this contact is kept filled by a source term from somewhere, so that electrons here continually go out, but then new ones come in. And so E minus H1 times phi is the wave function in this contact, is equal to the source term in this contact. And E minus H2, this is 0, because this contact is empty. Now, what with this minus I eta? Well, eta is assumed to be a small imaginary number. And what it ensures is that the wave functions in these contacts decay eventually, so that left to itself, they all go to 0. That is, usually what happens is, if a state has an energy epsilon, then the wave function goes as exponential of minus I epsilon t over h bar. But because of this minus I eta, you have this additional minus I eta, which gives this decaying part of the exponential. So what that means is, usually, if you put an electron in a state epsilon, it stays there forever, because you just have, the wave function looks like this. The phase changes with time, but psi star psi does not change. But now we have this imaginary part which gives this decay. So what that means is, if you wait long enough, the probability will become 0. Which is why in this contact, for example, the wave function is 0. Because left to itself, it just decays. The middle one, I haven't put in an I eta, so technically the wave function didn't need to be 0. But let's assume it's empty to start with, no electrons in there. And in the left contact, that's where we are assuming there is some wave function. Why? Because external sources continually put electrons in. That's this S1. So in this contact, also electrons leak out, but because new ones come in, you have a certain steady state number of electrons in there. So that's how we are setting up the problem. And for the moment, there is no connection between the three regions. And now what we do is introduce these connection between the three regions, which is this tau 1 and tau 1 dagger. Overall, this thing is Hermitian, so if you have a tau here, you must have tau dagger there. Similarly, tau 2 is the connection of the middle region to this contact 2, and the tau 2 dagger here. And when you connect it, of course, you still have the source term which wants to keep it at phi, but because of the connection, it will change from phi. There will be an additional part which I have written with this symbol, the chi1. And then there's the psi inside the device, and there's the chi2 in this contact. So you see, originally all you had was electrons in this contact, which were kept there by new ones coming in continually. And now that you have connected them, what happens is you actually have electrons inside the device, and the electrons in the contact are changed a little bit. There is some electrons in this contact, that's the chi2, and in this contact, it has changed from what it used to be. So these three then would be our basic equations. Okay? Remember, these are all matrices, And one point where, just to simplify the notation and being a little sloppy, is that you see this H is a matrix, and this H1 is a matrix, the tau is a matrix, and so on. So, whereas this E and this eta, these are numbers. So, I should really take E plus I eta and multiply it by the identity matrix, which are of the same dimension as H1. Similarly, here it should be EI, where I is an identity matrix with the same dimension as H. Right? But just to avoid clutter, I'm not writing that I. So wherever you see this E plus I eta, it's implied that it is multiplied by a identity matrix of the appropriate size. Okay, so we have these three equations. So what we'll do first is write them out one by one. So look at the last equation. So if you write it out, you get minus tau 2 dagger psi plus E plus I eta minus H2 times I2 is equal to 0. So you can solve this to write this chi2, because it's equal to the inverse of this times this quantity. So that's this expression. Chi2 is equal to this inverse times tau 2 dagger times psi. And that's what I will do. So next we'll look at the first equation. So that first equation is E plus I eta minus H1 times phi 1, E plus I eta minus H1 times chi 1. This is kind of what was there before we connected, and this is the additional part after we connected. And then minus tau 1 dagger psi is equal to S1. Now we note that you see this is equal to that because see, before you connected things, that's what you had. So you can cancel that out. So what remains is this part. And again, you can solve for chi1, and it will look like chi1 is equal to inverse of this times tau 1 dagger psi. So what we have obtained now is expressions for these additional terms in the contacts and related them to the psi inside the device. And now we write out the middle equation, which looks like this. It's tau 1 times phi 1 plus chi 1, E minus H times psi, tau 2 times tau chi 2. That's equal to 0. So what we now want to do is use these two expressions to replace chi 1 and chi 2. And when we do that, so we are using those two expressions, putting it in here. And when you do that, what you get is E psi minus H psi, that's E psi and H psi. And then this tau 1 chi 1, instead of chi you put that in, so you get sigma 1 psi. Similarly, tau 2 chi 2, that gives you sigma 2 psi. And this tau 1 phi 1, remember phi 1 was the initial wave function in this contact before you connected anything. And so tau 1 times that, that's this source term, S1. So S1 is equal to tau 1 phi 1. And the sigma 1 is tau 1 times this inverse times tau 1 dagger. Sigma 2 is like tau 2 times this inverse times tau 2 dagger. So that's sigma 2. So this is the point I wanted to stress, that when you started this NEGF, I said that you can start from E psi equals H psi, put in the boundary conditions and get to something like this, effectively. That what did the contact do? It put in these two sigmas and there's a source term that comes in. And yesterday we did a 1D example where I did this by just doing what was straightforward scattering theory, your incident wave, etc. This is a more general situation. So it's like, this is your device, you got these two contacts, but what always puzzled me, I remember in the beginning also, was that how could you start from something Hermitian, play around with it and get all these non-Hermitian things in there, sigmas, etc. And that's where this subtlety is, that you have to introduce this minus I eta into the H, into the contacts. Because this is a point I often make, that when current flows, you Electrons coming from the source into the device go out into the contact. But then, the reason you have a resistance is because what goes out into this contact then goes away from the device into a battery. And a new one comes in from here. That's a very important part of current flow. If that didn't happen, you wouldn't have a resistor, you just have a capacitor. What I mean is, some electrons would transfer from left to right, and after some time the flow would stop. Only reason current flows forever, continues doing it, is because the battery continually takes things out and puts things back again. And a lot of these microscopic models kind of almost try to avoid addressing that issue. That in your Hamiltonian, what is it that actually puts electrons in and takes them out? And yet, physically we know that if that didn't happen, you wouldn't have a resistor, you'd have a capacitor. And so often, a lot of the usual theories would do is, they would talk about AC transport, where you don't quite have a flow like that necessarily, kind of going back and forth. And then let omega tend to 0. But I think that doesn't quite get you the DC conductance always necessarily. But here you are kind of addressing it directly. And of course, this I eta represents that fact that there's a connection to a battery and which continually puts in electrons and takes them out. Anyway, but this is how the math would work. And at the end of it, what you now have is a general relation then, that you can start from this basic thing for your channel, and after you have connected it to the contacts, you pick up two self-energy terms and a source term. That's it. Okay. Any questions on this? Is this part?
So when people talk about the systems, they basically talk about the coupling limits, like whether the contact is strongly coupled to the channel or it is weakly coupled to the channel. Is that information is contained in that self-energy terms?
So that would be part of this tau. So we now have this self-energy, which is tau G, tau dagger. So the tau tells you the degree of coupling, because it is the matrix element between this and this. That's the tau. And the other information you need to get the sigma for the contact is this quantity, which is what is called the surface Green's function. Okay? And that again, there are general methods of doing it. So if you had a funny shaped contact with all kinds of, not a simple rectangular thing, again, there are well-defined ways of getting the surface Green's function for that method. So this would be the most general way of getting sigmas. You need a tau and the surface Green's function. And that would be it. Yes, I think we have now obtained a general expression, you see, for the source term. It's equal to tau 1 times the wave function that existed before you connected it. We have obtained an expression for the sigmas. What does it look like? Well, it's tau 1 times this inverse tau dagger. And this inverse, this quantity is what's called the surface Green's function, which we'll talk more about shortly. So that's what I'll write as G1. It's a property of contact 1. Note that it only involves the Hamiltonian of contact 1. Similarly, this is the surface Green's function for contact 2. It involves only the Hamiltonian for contact 2. So, what we have managed to do is, we have obtained a general expression now that looks just like what we had done for 1D in unit 2. That is, E psi equals H psi. That's the usual Schrodinger equation. But now we have put in these boundary conditions and come up with the outflow term and the inflow term. And we have obtained expressions for sigma 1, looks like tau 1, G1, tau 1 dagger. Sigma 2 is tau 2, G2, tau 2 dagger. And we have obtained an expression for the source term. And this then is like the generalization of this 1D result that we had before. So we now have an expression for the sigmas and the expression for the S. And I'd just like to make a little point about the connection between them. So sigma 1 is tau 1, G1, tau 1 dagger. Now if you look at gamma, the broadening function which is related to the anti-Hermitian part of sigma, then you could write it in this way. See, the sigma 1 minus sigma 1 dagger sigma 1 is tau G1 tau 1 dagger. So you could write it as tau 1 and then I G1 minus G1 dagger and then tau 1 dagger. By the way, this requires a little matrix algebra. You should try this out. And you have to remember that when you have the dagger of a product like AB, you have to reverse it. It's B dagger, A dagger. So to see how you get from this step to this step using sigma 1, you'd have to make use of that. If you do that, you'll get this expression, and then you notice that I times G1 minus G1 dagger is G is the surface Green's function of contact 1, but this is like the spectral function on the local density of states on contact 1. And so you get tau 1, A1, tau 1 dagger. So that's this gap. So this is the thing that I say is a lot like Fermi's golden rule. That what is the scattering rate? It's this density of states times the matrix element squared. But this is the general version of that. Now look at the source term. If you remember, we have this expression for this S1, and the sigma in is S1, S1 dagger. So you can put it in, S1 is tau 1, phi 1, and S1 dagger is phi 1 dagger, tau 1 dagger. And notice that what's here is like the electron density operator in contact 1. Remember, phi was this wave function that you had in contact 1 before you connected it. So this is like what you had in contact 1, electron density, before you connected it. And so that you could write as Gn for contact 1. Now, if the contact happens to be in equilibrium, then this Gn for contact 1 is related to its spectral function by the Fermi function. So it's like density of states times Fermi function is electron density. And in that case, you see sigma in is tau 1, A1, tau 1 dagger times F1, while gamma is tau 1, A1, tau 1 dagger. And so you get sigma in is gamma times F. And in general, when you're doing this, you have a contact. What you need is the sigma. That's the first thing. And we talked about this tau G, tau dagger. The other thing you need is the source term. But you don't really need the source term. What you need is its strength, SS dagger. And the thing is that that's really just equal to the Fermi function times the gamma for that contact. And gamma being, of course, the anti-Hermitian part of sigma. So once you have sigma, it's more or less done. You have the in scattered this source term just out of that because it's just gamma times F. So because this tells you the rate at which things come in, whereas this determines the rate at which things go out, and they are kind of connected. If you have a strong connection, electrons come in easily, but they also go out easily. That's all connected overall. Okay? So that's the general idea. Then this gives you the more general feeling of how it works. But I always first recommend just doing the 1D thing, where you're not using any advanced concepts. The math is easier, and you can see all of this much more clearly. But then this is how you could translate into any complicated structure, irrespective of the nature of the contact and so on. And as when you're doing electron-phonon interactions or other complicated things, again, up to here is still the same. It is just that this step wouldn't work anymore, because you wouldn't have a Fermi function times the density of states in that form. That you wouldn't be using. Right? Otherwise, the starting point is still the same kind of thing. Sigma equals tau G tau dagger.
So,
Yeah. Any questions, please? Yeah. Go ahead.
in that sigma in expression, the final result is tau 1, G1, and then tau dagger. So is that G surface Green's function or
Surface Green's function. Tau G tau dagger. That G is the surface Green's function, which means the contact, of course, is an infinite thing. So when you look at its Green's function, it's an infinitely large matrix. Surface Green's function means I just want the stuff on the surface. I just want this one. Nothing else. That is it. And that, as I say, if it's a rectangular thing, you can all get the G analytically. Otherwise, there are methods of doing this numerically. So I think the lecture after this probably goes through how you can find the surface Green's function for a given conductor. But this is the part that makes all of these calculations relatively, almost, I say that you do this calculation relatively straightforward. So it is not like you have to understand everything in order to do it. It's more like you do the calculation and then try to understand what you're doing. So you could look at this graphene example a little bit. Yeah, I think this is graphene. But I think there's a question about graphene, so you could look at that a little bit. On structure. Two different problems. Now, earlier, if you remember, that was in lecture 2 of this unit, we talked about how you could find the self-energy using this method of basis transformations. So the idea is, if you have a contact like this, and you think of it as 1D chain with these alphas connected by the betas, where alpha represents the entire column, beta is what connects one column to the next. And then for a square lattice like this, beta looks like an identity matrix, in the sense it's not only diagonal, but all diagonal elements are equal. Now, alpha has a non-zero upper diagonal and lower diagonal. But what you could do then is do a basis transformation here and make this diagonal, and beta, of course, still stays diagonal because it is essentially an identity matrix. And so once you have done a basis transformation, both alpha and beta can become diagonal. But this is not in general possible, because there are problems like, say for example, graphene, where we don't really have a square lattice, we have this hexagonal lattice. And in this case, if you look at alpha, I guess you could try to use this unit, for example. You could think of that as one column. So this is one unit, that's another identical unit, and they are connected by these three betas. So beta would be these three things here. And this would be your alpha, and that would be another alpha. Now in this case, beta is not an identity matrix. Here beta was an identity matrix because every element in this column was connected to a corresponding element in that column. So 1 got connected to 1, 2 got connected to 2, 3 got connected to 3, and equal. Here it isn't quite like that. When you look at this column, you got many elements here. One there, one here, one here, one here, etc. And this one is connected to that one, but this one's not connected to anything directly. I mean, that point on this column is not connected to any point on that column at all. Again, this one's connected to that. So what that means is when you try to write the beta, you won't get something like this. You won't get an identity matrix. You get connections for certain points and zeros for many others. And now if you try to diagonalize this alpha, the alpha you get for one of these units, with all these hexagons that you could write down. If you try to diagonalize alpha, beta would become something else. I mean, to start with it was diagonal, but because it wasn't an identity matrix, when you do a basis transformation, it won't stay diagonal anymore. And of course, if alpha and beta are both diagonal, then you can visualize the problem as lots of 1D problems in parallel, because they're both diagonal. But if one of them is not diagonal, then you don't have that luxury anymore. Then all these different chains get connected up. So for graphene, that's why you couldn't really use the method we had in lecture 2. But what you could use is the method we just discussed in lectures 3 and 4. Because in lectures 3 and 4, what we say is any structure that's described by alphas and betas you could first find the surface Green's function by solving this matrix equation iteratively. So this is the lecture I skipped. So the surface Green's function, how you find it. But that's also straightforward. It's this equation that you have to solve iteratively. And the lecture we just watched, that was talking about the sigma equals tau zeta, right? And then once you have this surface Green's function, you could write the self-energy by taking this tau g, tau I. So numerically, that is how you could handle this problem. So if you think of a sheet of graphene where carbon atoms are at these points, as you know, and you could think of current flow in this direction. So that way you'd have a contact here and a contact there, so you'd have a sigma 1 here, a sigma 2 over there, and those sigmas you could write down using this principle. Okay? And if you're interested in the details, you should look at the MATLAB codes that are in the notes, which describe how this problem is done. Now, so you could apply it to this problem, or you could apply it to, I guess, a different problem where the contacts are put in a different direction, for example. Now here, we call this usually the armchair edge. Now why do you call it the armchair edge? Well, if the current is flowing in this direction, and if you look at this edge, I guess with a little imagination, you could see why someone might think of that as an armchair. See, it's somewhere where, I guess you can imagine lying down on that. So that's why they call this an armchair edge. Now when you go at 90 degrees to it, which means supposing instead of the current flowing this way, you put your contacts in this direction, so you have the current flowing this way, then you call it a zigzag edge, because now it doesn't require much imagination. If you look at this edge, it sure looks zigzag. Right? So often these are the two limits that people talk about. Of course, you have to be careful because, of course, if this direction, if in the transverse direction you have an armchair, then in the longitudinal direction you would have a zigzag. And so you have to be careful when you are referring to something as armchair, which side you are talking about, this one or that one. Okay? And of course, you could always have all kinds of other orientations because your contacts could be at an angle like this. It doesn't have to be in this, either this way or that way, like the two limits that I've shown. These are the most common ones, but there can be all kinds of different angles. And in each case, though, you could write down these alphas and betas. That is, what you have to do is set it up, figure out in a 1D chain what each unit should be. So figure out the alphas and betas. Then you have to solve this iteratively to find the surface Green's function, and then you could find the self-energy. So that would be the overall procedure. Now I'll just show you some result that you could get, and as I say, the MATLAB codes are in the notes. So if you get the armchair edge, you get this black curve. And if you do the zigzag edge, you get the red curve. And what are we plotting here? Well, this is as a function of energy, the transmission. And this is for a ballistic conductor. That is, you're assuming you have a ballistic graphene, you have one contact here, another contact there. So we are plotting this transmission, and we chose a specific width in this case. I think it's about like 15 units or so in this direction. And the two, an armchair and zigzag, were chosen such that the width is approximately the same. So in this case, the width corresponds to this direction. In this case, the width corresponds to that one. And again, the dimensions were chosen, that they're about the same width. And what you find then is that when you look at the transmission as a function of energy, it's minimum right when it's in the middle, and then as you go in this direction, the number of modes increases, the density of states increases, and if you go below, again same story, density of states increases, number of modes increases, and one point to note is that there's hardly any gap here. This is the important problem with graphene in general that people talk about, that unlike other semiconductors, there's no gap, in the sense there isn't the energy range where you have like 0 modes ordinarily, because to start with, graphite is semi-metal. So it's like there's density of states on this side, density of states on this side, it's 0 only right there. And that, I guess, detracts from certain applications, like if you wanted to make a transistor and you wanted to turn things off, you want to put your Fermi energy in the gap. And so not having a gap from that point of view is a disadvantage. But all this, of course, would come out automatically from this NEGF method that we have been discussing. As I stated before, that the power of this NEGF method is that if you know what you're doing, to understand the procedure clearly, you can get numerical results without necessarily understanding all the physics of what is happening. And so you can use the numerics to improve your intuition and understanding. So what you should do is set it up properly, make sure you can calculate things numerically, and then see if you can understand what you calculate. So here, for example, one thing one could do is look at the semi-classical answer. So what do I mean by the semi-classical answer? Well, the semi-classical one looks something like this. What we discussed in Unit 1 is that when you look at the band structure of graphene, there are these multiple values. So this was discussed in Unit 1. And if you go to one of these values, right around there, you have a linear dispersion relation where E is proportional to K. K being measured from that point. Okay? And so if you want to look at one of these values, you could write E as a constant and Ka. Now, how would you calculate the number of modes? Well, roughly speaking, again, the idea is number of modes is the number of wavelengths that fit into the cross section. So if you have a graphene sheet whose width is W, and in the semi-classical description, it doesn't matter whether it's armchair or graphene or zigzag, because we're treating it as a kind of a continuum thing. So if it's of width W, then the number of modes is kW over pi. And that comes from this idea that how many half wavelengths fit into the width. These are the semi-classical arguments that we went through in part A of the course. So if you do that as kW over pi, now why the 2? Well, 2 is because in graphene there are these 2 values. And as we discussed again in Unit 1, there are kind of 6 values within a first Brillouin zone. But each value is a 1/3 value. So overall it's like 2 values, one around here and one around here. So the number of modes is 2 times kW over pi. And now if you use this expression, you could replace k in terms of E. And then you get this expression. So you get the number of modes as a function of energy, and it's a straight line. So that's what is plotted here. That's this straight line. So this is what you'd have got from a simple semi-classical argument. You get that straight line. And you can kind of see that the actual result follows that straight line roughly, at least at low energy. And we don't expect it to fit at high energies anyway, because this dispersion relation only holds for small energies around that value. So you don't really expect it to hold out here. But the interesting point is, until here it holds quite well. See? So this is an example I often suggest to go through. Because, as I say, with NEGF, you have just set up the Hamiltonians there with all the atoms in that lattice. And you don't have you're not feeding in this idea about values or anything else. You just fed in the basic atomic structure, that's all. And when you run it, you automatically get this, the transmission. And this, of course, again, you have to set it up just right, because As I say, steps like this don't occur if you have even a simple error somewhere. Kind of everything has to be right. And these you can look at the codes. And you can see there's a difference between armchair and the zigzag when you do the atomistic simulation. On the other hand, at a semi-classical level, it's basically a material with a dispersion relation that looks like so. And then you would expect this straight line based on the simple argument that how many wavelengths fit into the cross section. And that describes the basic result fairly well. See? So this is I've always felt a very good example to go through this straight line. And of course, what the straight line isn't showing is all these steps. Because the straight line is assuming, treating this just as a number, not taking its integer value or anything. So you don't expect the steps, you just get the straight line. Now, again, the point to note is that when you do the numerical method though, you don't have to make all these arguments. You don't have to understand how many values graphene has, for example. So here, in order to get the semi-classical answer, I have to put this 2 in. Where did the 2 come from? Well, 2 because there's 2 values. How do I know there's 2 values? Well, because when you look at the first Brillouin zone, there's actually this 6 minima, and each one is a 1/3 value and so on. Remember, we had a long discussion. So it takes a lot of understanding, a lot of discussion to come up with this expression. Okay? That's kind of what we did in Unit 1. But numerically, you see, this plot came without understanding any of that. Numerically, how did we get it? Well, we just set up graphene, wrote down the alphas and betas, found the surface Green's function, found the sigma, and numerically that's how we got it. So when you have a new material where you don't understand all this yet, you could still use the numerical method. But then what you should do is go through all the arguments properly and see if you can understand what you're calculating. Now numerically, the other thing you can do is, easily is, instead of graphene, you could be looking at carbon nanotubes. You see the difference between graphene and carbon nanotubes is, graphene is just a sheet like this, whereas in carbon nanotubes, it's rolled up in like a straw. Right? So you have this periodic kind of boundary condition along the width. So here what I've shown is graphene. In carbon nanotubes, what would happen is this end would get connected to that end again. Now numerically that's easy enough to do. That is, when you write the alpha, you just connect this end to that end. That's all. Similarly, for zigzag edge, you connect this end to that end. You think of it as if it's rolled wrong. So numerically, you could just change the alphas and betas. And if you look at the MATLAB code, it just takes one line to do that, where you make that change. And if you do that, you'll get a different transmission. You see, so we are plotting the same thing here, transmission, but now you'll notice the steps are not quite as fine as this one. Roughly speaking, with periodic boundary conditions, you tend to get less number of steps, but the steps itself are bigger. So again, it follows roughly the same semi-classical line, but the details are now different. And when people look at small structures, indeed, they see these differences experimentally as well. So that was then I guess, I think, yeah. So, yeah, questions please. I think what we tried to go through yesterday was the elementary part of energy, the 1D examples. And what I tried to give you a flavor of here was the advanced part, which means how to do general problems. Okay? That's it. And general problems involves this sigma. Now the part I didn't discuss too much so far, and we could have more of that in the discussion, is how to include dephasing processes. That is, in general, as I said, there's a sigma 1 and sigma 2, which represent the two contacts. And then you could also have a sigma 0, which represents interaction with the surroundings. And there you can use different expressions for sigma 0 to give you different types of interactions. That's also again in the lectures. If you have interest in that, we could talk more about that. But otherwise, our general plan would be after this to get into spin transport. To talk more about spin. And so maybe what we could do is, I guess, yeah, it's 11:30.
Yeah, we'll be back here.
But,
Okay.
yeah, we could start a little later.